Hi everyone, it's Mr. Strickland. In class we've been discussing different ways to represent situations and events that we encounter in the natural world. And I wanted to start off by reviewing very quickly the 4 ways that we've been representing relationships between variables. One of the first ways is just simply with language. We can describe things verbally or using the written word. We can use algebra, mathematics with some formula. We can diagram a situation, and we can describe a situation using graphs. And graphing is the subject of today's video. I wanted to let y'all know here early in the beginning of the year that there are some graphs that are very common in science. There's just some the shapes to graphs that we see over and over again. There's not as many as people might assume. We're going to go over some of these common graph shapes. So that you know specifically what I want y'all to learn, I'm going to lay it out for you. What I want you to get out of this short video is just simply to recognize the shapes of the different common graphs that we see, because each shape is unique. And I want you to attach a common name to that graphical shape. So it's just that simple. I want you to recognize the shape and attach a name to the shape. Now I'm going to give you guys the formula that describes the relationship, but I don't want anybody to stress over that. When we have our test, at least this first one, that's not going to really be a big deal. So the big deal is to recognize the shape and put a name with the shape. So let's jump right in. The first graph is probably the one that you are most familiar with, graph of a linear function. Linear functions have the form of y equals mx plus b. You guys are familiar with that. M is the slope and b is the y-intercept. Now, so this might be a line or a linear function that you would have played with in algebra, but I'm going to back up. What we normally use in science, or at least here at the beginning of the year, we may graph distance and time and call it speed or velocity, but we can have a positive slope and have a speed graph that looks something like that. If we have an object that starts away from us and then closes the distance toward us, it could have a negative slope and look like that. I'm not going to spend a lot of time with this sort of graph because I think this is the one that you're probably the most familiar with, and you can use your valuable time listening to other things besides me talk. So I'm going to move right on into the next one. The next type of graph that we see quite often in science is an inverse function, such as y equals 1 over x. And the shape of this graph is pretty simple. Quite often it looks something like this. Now you'll notice in this inverse function that the graph doesn't touch the y-axis. Examples of inverse relationships are things like pressure and volume, mass and acceleration. Let's take a look at that. Let's say we've got the volume of some gas and we relate it to the pressure. Well, as the volume of a container increases on the x-axis, you'll notice that the pressure decreases. So when you have an increase in volume, you have a decrease in pressure. Same thing could happen with mass and acceleration. Let me clear this really quickly. Whoops. Well, I'll just redraw the graph. So here we have this graph again. Well, the acceleration of an object, possibly, as the mass of an object increases along the x-axis, the acceleration of that object decreases. Very common relationships that we see over and over again in science. So I want you to become familiar with that shape. And moving right along, now we have the power function. Now power functions have the shape of y equals ax to the b, where a and b are constants. They get their name because x is raised to some power. Now there's many physical laws that are described by the graph, gravitational force, the dimming of light with distance. I mean, there's a whole slew of things that are power functions. But let me give you the basic shapes of the graphs, because after all, that's what I wanted you to really get today. Now, if we have something like, let's say we have a graph like y equals x squared, then we're going to get this nice parabola. You guys are probably familiar with these parabolic shapes. Now, what we tend to see when we look at it in science, though, I mean, we tend to only work with that part, but I'll leave both of them up there. Now, if we have a graph like y equals x to the fourth, then the graph tends to be flatter at the bottom, but then move up more steeply. But it still has that parabolic shape. Now, one of the things you might see also, what if y equals x cubed? What if the power is odd? What we can see in that situation is perhaps a graph that looks like this. So those are the common shapes of power functions. Moving on to the next one that is quite common that we'll see are exponential functions. Now, exponential functions are y equals ab to the x, where x is the exponent. Now, these are really, really common in science. Things like population growth. If we have an animal, or particularly like a bacterial population growth, you might notice this graph will touch the y-axis too. But let's say you've got some population of organisms, and if they grow exponentially, then you get a graph that's shaped like that. So like bacteria, things like that can grow. Now you'll get this shape of graph when b is greater than 1. Now, along with this exponential function, we get exponential decay. So I want you to know what it looks like if b is less than 1. And examples of that might be things such as how far does light penetrate down in a muddy lake, or the radioactive decay of something like a carbon-14 isotope, and we're trying to date dinosaur bones. Well, now the graph you may see there is something where it starts at some number and then it gradually declines. So those are exponential functions, and you run into those really often in science. Moving on to the next one are logarithms. Logarithmic functions. I'm going to stick with a simple function like y equals log x. Logarithmic functions can describe things such as a response of the human eye to sounds, or the human ear to sounds, or the human eye to light. And those graphs have an interesting shape. They start out and then tend to level off pretty quickly. So when you see a graph like that, you can recognize that as a logarithmic function. And the last one I want to move on and talk about are periodic functions. Now these are functions, a function is periodic if the dependent variable or the y-axis repeats itself over and over as the independent variable increases and decreases. These are sorts of things like, I'll make these dots a little bit bigger, maybe where y'all can see them. We start at 10, There we go. If those are our points on this graph, then we could end up with this nice curve. It looks like that. And we see the examples we see of periodic functions are things like waves, rotary motion. So if you're looking at the motion of an electric motor, a wheel, rotation of a planet, many of those sorts of things are periodic in nature. And I say I didn't give you the notation. So these are sinusoidal functions. So if A sine of the bx plus c is the formula for that. So there you go. This video is pretty short and sweet. To remind you again, what I want you to get out of this is recognize the shapes of the graphs and then the names of the graphs. If you get those two things, you'll be looking at that on a test coming up soon. But the main point is, as we graph data through the year, you'll start to see the data fall into these common patterns. And when you see the patterns start to emerge, then what you start to realize is you know what the generic formula is for the relationship between your independent and dependent variables. And that's really the point, is to recognize the shape and then have some intuition about what the formula will be. So these are your basic functions, and I'll stop this and we'll discuss this in class more tomorrow.